We now have all the tools that we need to establish a way to narrow down the possible roots of a polynomial. Really well, actually. This only applies to rational roots, so irrational numbers like the ones that come out of the quadratic formula, for example. This is not going to help us with those. But it is going to give us a really good way to get started on looking for factors to a polynomial. This is the rational roots theorem, and it tells us that if we have a rational number, a fraction, that is a root of a polynomial with integer coefficients, so this only works for polynomials with integer coefficients, and again, it only applies to rational roots. So here we have our polynomial, right, written in that summation form. Right. The ANs are the coefficients, and they're integers. Then P, numerator, is a factor of the constant term. And Q, the denominator, is a factor of the leading coefficient. So what this is going to do for us is let us narrow down what the possible rational roots are. Notice this doesn't say that if we have any fraction like that, it's going to be a root. Just if we have a root, it's going to be a fraction like that. Okay, here's why. So if P over Q is a root, then the factor theorem that we saw previously tells us that Qx minus P is a factor of P. You might notice that we're doing that thing again, where we have a capital P and a lowercase p, and they mean something different. Again, capital and lowercase letters can represent different variables. It's a thing that happens all the time. So, Qx minus P is a factor of the polynomial P. So that means Qx minus P times some polynomial Q gives us P. Now we want to think back to what we know about multiplying polynomials. To get the leading term of P, we multiply Qx, the leading term of this factor, by the leading coefficient of Q, the other factor. But when we multiply the terms, we also multiply the coefficients. So Q is a factor of AN, which is the leading coefficient. We multiplied Q by something to get AN, so Q is a factor of AN. That's just what it means to be a factor. In the same way, the constant term of P is negative little p times the constant term of Q. Right now, the negative sign might throw us off a little bit, but when we're talking about factors, well, we can make them positive or negative because the other factor could be either positive or negative, so that negative sign is not going to trouble us. P is a factor of A0, the constant term of our given polynomial. And that's it. So just looking at the coefficients this way, that's the result that we wanted. Okay, how do we apply this? The thing that this does for us is that it lets us come up with an exhaustive list of all possible rational roots. So in this example, here's our leading term. Our leading coefficient is 6. The factors of 6 are 1, 2, 3, and 6. but we could have a positive or a negative value. The factors could be positive or negative. Our constant is negative 15. The factors of 15 are 1, 3, 5, and 15. And again, those could turn up as positive or negative, which means the possible rational roots are every possible fraction we could make with this. So Q could be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. P could be plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 15. Every possible fraction P over Q. So we've got, I'm going to leave out the plus or minus just to not write it over and over again as I'm making this table. But we've got 1 over 1 is 1, 3 over 1 is 3, 5 over 1 is 5, 15 over 1 is 15. 1 over 2 is 1/2. 3 over 2, that's 3/2. 5 over 2, 5/2. 15 over 2, 15/2. 1 over 3, that's 1/3. 3 over 3 is 1. 5 over 3, that's 5/3. 15 over 3 is 5. 1 over 6, that's 1/6. 3 over 6 is 1/2. 5 over 6, that's 5/6. 15 over 6 is 5/2. One thing you notice here is that all of these fractions that we ended up being able to reduce, those are numbers that we already had on the list. 1/2, that showed up here. 5/2, that showed up here. So sometimes we get something showing up on the list twice. That's good. That reduces how many things there are on the list. Because we have positive or negative 1, positive or negative 3, positive or negative 5, positive or negative 15, positive or negative 1/2, 3/2, 5/2, 15/2, 1/3, 5/3, 1/6, and 5/6. So we listed 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 numbers, but we have the positive and the negative version of each of those. So there are actually 24 possibilities. Now, 24 possibilities seems like a lot, but we've now narrowed it down from all of the rational numbers, every possible fraction we could write, to just 24 rational numbers. We can now make an exhaustive list of all the possible rational roots of a polynomial. And from there we can use trial and error to try to get to something smaller, which is what we'll see in the next video.